The concept of space-based solar power has been floating around for more than 70 years. Simply put, it's the idea of collecting solar power in space and beaming it down to Earth. Many of you may find this concept to be very outlandish, but why then has the US Navy in May of 2020 launched the first experimental solar satellite to do exactly that? We will cover this and all that you need to know about space-based solar power in this video, so make sure to watch it till the end. On this channel, Synergy Files, we aim to inspire people for a better, more sustainable world. Subscribe today to get the updates of all our latest videos. Space-based solar power, or SBSP in short, has remained in the consciousness of scientists ever since the idea was made public in a science fiction story written by Isaac Asimov in 1941. Over time, there has been extensive research on it, which was accelerated during the space race. Patents were filed and designs were finalized until common sense prevailed. It was realized that unless we bring down the cost of payload by an order of magnitude, this project will remain a novelty, a pipe dream, and a sci-fi fantasy. The development of SBSP rests on three different technologies. First is the space launch technology, second is the solar power conversion or the solar cells, and finally the wireless power transmission technology. Each time there's a breakthrough development in any of these areas, talks and speculation on SBSP go up. For instance, the recent success of the Falcon Heavy launch vehicle by SpaceX was followed up by many articles that reviewed the SBSP concept. This begs the question, why is it so attractive that we seemingly visit the concept of space-based solar power on every opportunity we get? It turns out that there are quite a few advantages of SBSP that are unique. Number one, we can get clean, emission-free energy 24/7, 365 days a year. More precisely, 99% of the times during the year. Secondly, we can direct energy to where and when it's needed very easily. The third advantage is that contrary to the popular belief, it has minimal plant and animal life interference if designed to certain parameters. Fourth advantage is that the satellite could be scaled up in modular fashion while remaining functional at all times. So the concept does have its merits and is technically feasible. It is, however, the economics that are challenging. And to see how big of a challenge it is, let's have a look at some numbers. First is the payload launch cost. Although this has come down significantly in the recent past, owing largely to private players like SpaceX and Blue Origin, it is still high. A kilogram of payload now costs around $2,720 to launch into lower Earth orbit. This is a huge drop when compared to the cost recorded between the 1970s to the year 2000, which was on average $18,500 per kilogram. It has to be noted that the figure for launch cost that makes SBSP feasible is merely $200 per kilogram. This figure of $200 per kilogram presumes that we will have solar panels with energy density of a kilowatt of power for just 5 kilograms of solar cells. Even with these heavily discounted numbers, it would cost $4 billion to put 4 gigawatt space-based solar power plant. For comparison, the new coal and nuclear power plants would cost $3 to $6 billion per gigawatt. What this is pointing to is the fact that if we can reduce the cost of SBSP, then it does make sense, particularly when compared to other power plants that have longer downtime and higher running costs. Now we can do two things to bring the cost down. First is to bring the launch cost down by tenfolds. The other is to reduce the weight of the cells to make a certain amount of power, that is to increase the energy density. The solar cells used in space are very efficient compared to terrestrial solar cells. Just 6.7 kilograms of solar cells for space application can produce 1 kilowatt of power. This is almost 5 times higher energy density by weight when compared to the panels used on our roof with the added weight of frame and glass. Scientists are optimistic in bringing down 6.7 kg of solar cells per kilowatt to just 1 kg of solar cells per kilowatt of power. This line of pursuit for now is less challenging than bringing the launch cost down. If this were to happen, then the cost of putting a 4 gigawatt power plant would be $8 billion at $2,000 per kilogram of payload launch price, making it comparable to the cost of new coal-based power plant. So it seems that we are approaching economic parity. There are also non-rocketry based launch options being looked at, such as the Skyhook, air launch and orbital airship that could reduce the payload launch cost significantly. It has to be mentioned here that if there was one person who had it all what it takes to do this, it would be Elon Musk. He has both solar power and space launch technology at his disposal, not to mention the capital required. Elon, however, has made it abundantly clear that he has no interest whatsoever in pursuing this. He is rather annoyed by the idea based on the fact that there are multiple layers of energy conversion involved. Sunlight has to be converted to electricity, which then has to be converted into microwaves, which in turn has to be reconverted into electricity, and at every step a portion of energy is lost. This also brings us nicely to the power transmission technology for solar satellites. There are three ways of transmitting power wirelessly from space. First is through microwaves. This is an idea that has been thoroughly tested on the ground and with great success. Efficiencies of over 95% have been realized. However, the microwaves have to be above a certain wavelength to be human and plant safe. The energy carried by them should not exceed 1 milliwatt per square centimeter. This means large rectifying antennas are required to receive them. For example, in 1978, NASA's study of solar power satellites required a 1 kilometer diameter transmitting antenna and a 10 kilometer diameter receiving antenna for microwave beam at 2.45 GHz. The cost of receiving station has been estimated to be $1 billion for 5 gigawatt power capacity. Laser is the second option that has its advantages. It will reduce the area of the receiver and there will be no radio frequency interference as power is transmitted. And also because of the narrow beam cross-section nature of lasers, there is little or no reduction in power when increasing the distance from transmitter to the receiver. There are drawbacks of lasers too. It requires a direct line of sight to the receiver. In the case of cloud cover, there is a chance for 100% power loss. Then there is the fact that it is hazardous to humans. Military use of high-powered laser beams has been explored, so there's that too. The depiction of alien aircraft firing huge beams of energy to destroy cities in movies doesn't really help the case of SBSP among the general populace, although preventing its misuse can be ensured by an international safe space energy protocol that every nation has to abide by. The third way of transmission is just reflecting light to a station on Earth using mirrors. It has the lowest setup cost compared to other methods, but has disadvantages of both microwaves and lasers in that it is less energy dense and requires a clear line of sight. It must be mentioned here that both China and Japan are actively pursuing space-based solar power, and they have already laid out the roadmap for doing so. There is one possible route through which the use of SBSP can be accelerated. That is by making solar cells inside the International Space Station from the waste that is generated by the space station. We are aware that solar cells can be easily printed on substrates. We are also aware that flash graphene can be produced easily from organic waste, and organic solar cells have made significant progress in the last decade. Bringing these technologies together to make solar panels in space will not only eliminate the waste containment problem in the ISS, but will also minimize the cost of putting solar panels in the lower Earth orbit. The US Naval Research Lab in May of 2020 has launched a small photovoltaic module through the X-37B. It is called the Photovoltaic Radio Frequency Antenna Module, or PRAM for short. The experiment is intended to analyze the antenna's energy conversion process and resulting thermal performance. Based on the data that will be gathered from this microwave-based energy transmitter, the plan is to scale up the system to meet the energy needs. One thing is for sure, each passing day our technological advancement is shrinking the economic hurdle that has kept this technology at bay. The proponents of SBSP say that the cost of this technology should be weighed against the cost of climate change. In other words, the cost of doing it should be weighed against the cost of not doing it. This way the perception would change and make the space-based solar power look more feasible. As for me, I believe there is plenty of low-hanging fruit if you want to tap renewable energy before focusing on SBSP. However, we should keep developing this technology so that in future, if there is a requirement due to overpopulation or natural disaster, then we can certainly use it to offset the fossil fuel-based power or any other power source that requires a huge supply chain. So what do you think about this idea? Is it worth pursuing SBSP or should we invest in other solutions? Do share your thoughts in the comment section. And with this, the video is concluded. If you learned something from the video, do give it a thumbs up. It helps the channel to grow. Thank you for your attention.